We'll continue our discussion on the force and energy relation. And what we have seen is that there is a special class of forces called center forces, which are conservative forces. And in that case, one can define or one can associate a potential energy function, which is a scalar quantity, related to that particular force. Right? Okay. So now what we have is, we have a special class of motion, which is termed as simple harmonic motion, and we have studied that earlier also. Right. So this class of motion arises because of a particular central force. Right. So all systems under action of this kind of force will perform periodic oscillatory motion about a point in space, which is termed as a simple harmonic oscillation. Right. And what I'm going to do is, in the next few lectures, I'm going to cover this problem in slightly more detail, right? And then we will move on to a different topic. Okay. So the center force responsible for the simple harmonic motion is F equal to minus KR R cap, right? And this is the nature of the force, that basically the force is attractive, or it always pulls the system towards some central location. Right. Could be origin, could be any other central location, and it's directed along the radial coordinate, right? Or in one dimension, this is always directed towards the origin or that particular point. Okay. Now, since this is a central force, it's a conservative force, so we can define a potential energy function associated with it, and we know now how to write down this potential energy function. So what I'm going to do is, so we normally wrote del of u is equal to path integral of f dot dr, and of course we know that the path integral is independent of the path taken, so integral f dot dr. Right. Now here, for time being, we'll just recall from our previous knowledge that the potential energy is a scalar quantity whose absolute magnitude as such does not matter, right? So the system actually responds, or the effect on the system is always seen in terms of differential potential energy at two different instances or at two different locations, right? So I can also write it down as minus u of r, right, in some proper coordinate system. Minus u of r is equal to integral f dot dr, and now putting the value of, for this particular central force, I can write down u of r as half k r square. So this is the potential energy associated with this kind of a force, right? And now we can, once we know the force, we know the potential energy, we can try to see the evolution of the system in time. Okay. So now let's do that, and we'll do that in one dimension, because anyway this is a central problem, so it's only the one coordinate which is responsible. So whatever we do for in one dimensional system is also valid, and we can extend it to other dimensions. So let's discuss simple harmonic motion in 1D. Okay. And now what we have in 1D is, we already said that f is of that kind, minus k of, let's say, x, and now again this is x cap, and of course now there is only one direction, so as such I can also drop the vector and just write down f equal to minus kx. If this is the case, then now I can start solving this. So I will do this, and now I am going to drop the vector sign. So m d2x over dt square is minus k of x. This basically is a second order differential equation, homogeneous in nature. D2x over dt square plus k by m x is equal to 0. Right. So it's a second order, right? There is double derivative, homogeneous differential equation, right? So this is the equation of motion, and now we can try to get the solution for this. So let us say that the solution for this x of t is something of this form. Okay. Where omega naught is simply k by m. Right, I have taken this as omega naught. So let's say this is the solution for this equation, right? And now, of course, we can quickly check by putting the value of x here in this equation and see if it satisfies this one. And I mean, it's rather obvious that you will see that it satisfies. Now, of course, what we have to do is we have to also find out these constant b and c. Right? And the way we can find out this constant is now we need some more information from the system or about the system, right? So that information is in terms of let's say at time t equal to 0. So initially, what is the initial state of the system, right? So we need what is the position of the system or the actual state of the system at time t equal to 0, and we can also look for its instantaneous motion. So what is the velocity of the system, right? It's moving or so it's moving with what magnitude and what is the in which direction, right? So is it going away from the center of the force or towards the center of the force, right? So if these two conditions are known, then with these two initial conditions we can find out the general solution for this equation. Of course, there is also a property of the differential equations that the order of differential equation will determine how many independent conditions you require or how many initial conditions you require to get the proper solution for that particular equation. It's a second order one, so we need at least two conditions. So let's try to write it down, and let us say that, so we'll write down a general solution. So let us say t equal to 0, it is at some location x0, and at t equal to 0, the velocity or x dot is v0. Okay, so this is the case. Now we can put these values. So again, now what we have is basically what we are saying is that this is a known quantity, this is a known quantity, right? So now we can use this, put it back here and solve for b and c. So if you do that, what we will get is we will get two equations, b plus c equal to 0. So this is equation number 1. Oh, sorry, not 0. b plus c equal to x0, and b minus c is equal to v naught over I omega naught. Okay, so these are the two conditions that we have on b and c, and now we can solve for b and c. If you add the equations, you can get the value of b. If you subtract the equation, then you can get the value of c. And what this gives us is the and then we can put back there. So you can do this. So solve for b and c, right? And now what will happen is we'll get this term. The values of b and c will come in terms of x naught plus minus I v naught omega naught. And what we can do here is we can also expand this exponential I omega naught t into cos omega naught t plus I sin omega naught t, so that we can cancel out or separate the terms containing this imaginary number I, and you can rearrange. I am going to write down the solution. So the solution will be x of t is equal to x naught cos of omega naught t plus I think v naught over omega naught. Let me just check. Yeah, sin of omega naught t. Okay, so this is the solution for a one-dimensional simple harmonic oscillator. And what I can do is I can further compactify it. So I can write it down. So I'll write it down as x of t as cosine of omega naught t plus phi. Okay, so I've compactified it like this. where A is, so now you could, with back substitution you can confirm that this is the correct form for x of t is x0 square plus v0 square over omega naught square. This is also termed as the amplitude of oscillatory motion. Okay. Phi is tan inverse minus v naught over x naught omega naught. This is termed as the phase angle or phase factor. Omega naught is, as we said before, square root of k by m is the natural frequency of oscillation and the time period t is related to this natural frequency. So time period t is in 2 pi by omega naught is then the time period. Okay. So this is our solution for a simple harmonic oscillator. And now once you have the solution, we can find out the velocity, acceleration at any given point of time, and have the entire and have complete knowledge about the evolution of the system. Okay. Now, what we can do is we can see like what does basically this space factor means. So the space factor basically determines what is the original amplitude, what is the initial state of the system, right? So for example, let's say at t equal to 0, let's say x of t equal to 0 was the amplitude, right? So that means the to begin with, the particle was at one of the extremes in its motion, right? So if this is the case, then putting it here, we can see that if that's the case, that means x of t equal to 0 is a cos this term will go to 0 and cos phi, and since this is 0, that means and since this is this thing, that means cos phi equal to 1 and cos phi will be 1 when phi equal to 0. So this will imply that if this is the initial condition, that means the phase angle is 0, and now I can plot it. So I can plot the position x of t as a function of time. This is the 0. Let's say this is the amplitude, and of course it makes oscillatory motion. You can see that the solution has a trigonometric term cosine of omega naught t plus phi. So this will be bound between plus minus 1. That means the motion will be bound between plus minus a. So then, and now at t equal to 0 we said it's a. So it starts from here, right? And then simply keeps making this kind of oscillation sinusoidal functions. Now in this case, we have defined that this is the amplitude. So this is the trajectory, or this is the xt graph. Then this will be the amplitude of motion. This time is the total time period, okay, of the oscillator time period, where the material system attains the exact same state as from any other given time t. So that's the time period. And now to look at where is the phase factor here, let me say that in some other instant at t equal to 0, or I have started measurement at t equal to 0, when x of t equal to 0 was not a but a by 2. Okay. If that is the case, then by putting it here, we can see that this will imply that phi is 60 degree, right? And now the way this curve is going to develop is, in that case, my system is going to start at a by 2, because I said that t equal to 0, the amplitude is a by 2, and then it's going to follow the exact same motion, right? It's still bound by that plus minus 1, so it's going to follow the exact same motion. However, it is simply going to be slightly off from this location, and then this blue curve is the. So the phase factor basically gives us an original reference, and fixing this one, we can see how different scenarios can develop. Okay. So this is about the solution for simple harmonic oscillator. Okay. Now what one can do is we can also find out the energy of this oscillator, right? Because again it's a central force system, so we already know how to write down its energy. And first of all, what we know is total energy of the system is constant, right? And what is the total energy? E is kinetic energy plus potential energy is equal to some constant, right? Now what is the kinetic energy? It's half m v square instantaneous velocity at any given instant plus half k x square, right? We just found that for central force of kind minus kx, this is the potential energy, right? And if this is the case, then of course this is also x of t. So now this is the form, and we can write it down in slightly more detail. So again, you already know that x of t is a cos omega naught t plus phi. So this implies v of t will be minus a omega naught sine of omega naught t plus phi. This is the first derivative of this, and now we can put these two back here and write down an expression for the total energy. So this will be half m v t square, so a square omega naught square sine square omega naught t plus phi, right, plus half k x t square. So this is a square cos square omega naught t plus phi. We can replace this k as m omega naught square. Okay. So I will simply replace it here, and this rearrangement will let us take some terms out. So m omega naught square, we can take this entire term out, half m omega naught square a square out, and you can see that then this is sine square omega naught t plus phi plus cos square omega naught t plus phi, which is basically equal to 1. Sine square theta plus cos square theta is 1. So the total energy of a simple harmonic oscillator at any given instant of time is a constant. Mass is a constant, natural frequency is a constant, and amplitude, which is the maximum range of motion, is also a constant for that particular system, right? So the postulate that we started with, yes, for a simple harmonic oscillator, the total energy of the system will remain a constant. Okay, so this is a constant, and the total energy will be given by this one. So it basically depends on the parameters of the system. Now again, what we can see is, if you look at this, let's say this expression, so the total energy, which is a constant, is governed or not governed, is given by sum of kinetic energy plus potential energy, and both have this kind of oscillatory function, right? So that means at any given instant, there will be part of total energy given as kinetic energy, rest as potential energy, and this is going to change between the maximum and the minimum, right? In fact, this is going to go between kinetic energy can be completely the total energy, potential energy will go to 0, and similarly kinetic energy will be 0 and potential energy will be the maximum energy, because sine and cos both functions will oscillate between plus minus 1 going through 0, right? So there will be partitioning of energy. So now what we can do is, so we cannot, of course, for every instant we'll have to find out what is the kinetic energy, what is the potential energy. But what we can find out, or what we can also tell about the system is what is the average kinetic and potential energy, right? So let's say over one cycle, we know that if the motion is periodic, so let's try to find out over one cycle, although at every instant the total energy remains constant, what is the average kinetic energy in the system and what is the average potential energy in the system, right? So the average kinetic energy represented like this, and how do we find it? So we write it down as the kinetic energy as a function of time, right, integrated over one time period 0 to t divided by the time period d. So this is the definition of average kinetic energy or potential energy, or rather any average function. In fact, if you look back, we wrote something similar when we were discussing the impulse formalism, that integral of f dt is called the impulse, right? And there we define that if we can find out the integral of f dt, then we can find out some kind of average force acting on a characteristic time scale, right? So this is the same, this is similar to that. So average kinetic energy is given like this, and now we can find it out because we already know what is the kinetic energy as a function of time. Let's say integral 0 to t, and instead of kt we just simply put it here. So half m omega naught square a square sine square omega t plus phi over integral of 0 to t d, right? And now here we can see that since there is an integral, all these terms are constant, they are not dependent on time, so they are not going to do anything inside the integral. We can take them out, half m omega naught square a square, and the integration is only over the sine square function. So sine square omega naught t plus phi upon integral 0 to t d, which is only going to give us the time period t, right? Now this is a very simple thing. Now what you should check is, or you may have seen it earlier, that this quantity integral of basically this is similar to integral 0 to 2 pi sine square theta d theta over integral 0 to 2 pi d theta, right? So something like this. So this integral is actually equal to half. If you have not seen it earlier, if you have not encountered this earlier, you can solve it. It's not a big concern. You can convert this into, well, just check 1 plus minus cos 2 theta kind of form, right? And then do the integral. This is dt here. Do the integral, and again confirm that this entire quantity simply gives a factor of half. So that way, what I have is the average kinetic energy stored in the simple harmonic oscillator over one time period is basically 1 by 4 m omega naught square a square, and this is nothing but the total energy, right? Of course, I can also write this down as half of average total energy, but this is exactly the same because the total energy is constant, right? Okay. Very quickly, we can, so we can also do the same thing for potential energy. All we have to do is put in this term. Of course, this term is same, so nothing happens. We'll have to get the average of cos square omega naught t plus phi over one time period, and what we'll see is exactly same as the sine square function. This is also going to give us a factor of half. So this is going to come out exactly same as the average kinetic energy, and both are going to be half of the total energy. So this is an important property of systems under central force of the kind minus kr or minus kx, or systems that are going under simple harmonic oscillation, simple harmonic motion, that their average kinetic, average potential energy is same, is exactly half of the total energy, and the total energy of the system remains constant.